So, good morning, everyone. Yes, I'm Olaf, and today I'm not going to be talking to you guys about guitars, but about design for additive manufacturing in particular. And particularly, the focus of today is, to me, design for additive manufacturing. A lot of companies think of it as a luxury, as a nice to have, but I'm hoping to sort of demonstrate that it's not actually a luxury, it's a necessity. You must design for additive manufacturing if you want to take advantage of the technology and use it in the best possible ways. So, we're going to be looking at some of the cost of additive manufacturing. What determines the cost? Because if you understand what determines the cost, then you can start to design for it. And always good to start with the growth. The growth in additive manufacturing, this is from the Waller's report, is tremendous. Growing sort of close to 20% compound annual growth ongoing. 2015 in Sweden, we spent more in 1 year than we spent in the last 2 decades combined. Same again last year. That growth is tremendous, but there's a but to this. I've been thinking about this a lot over the last 2 years. A lot of this growth is driven by very high-end industry, aeronautic industry, ESS, MAX 4, industries in which cost is not really that much of an issue. Whereas if you look at regular, normal companies, the growth has not actually been that tremendous. The uptake of additive manufacturing has not been nearly as high in regular companies as it has in the high-end, high-value industries. Medical, again, if a medical implant, how much it costs is not that important compared to the benefits it offers. The same on an airplane. Saving weights far outweighs the increased cost of the component. And to my mind, the one reason why the adoption among normal companies has been pretty slow is cost. Particular with metal additive manufacturing, but the same multiplies to polymer additive manufacturing, ceramics, and so on. The cost, to my mind, today is prohibitively high. And if we understand what determines that cost, particularly with metal parts, we can then start to design the parts to minimize that cost. And that's what I'm going to start off talking about today, and really whether it's feasible or not to print parts without designing for additive manufacturing. So really the one thing that determines the cost of additive manufacturing is it's essentially a very slow process. It's a serial process where you build layer upon layer upon layer, as opposed to conventional manufacturing. Injection molding, you shoot all the plastic in at once, in a few seconds you're done. And the cost is largely driven by machine cost. Your hourly machine cost for a metal printer averages out to about $65 an hour. Let's say if you got a 750,000 euro machine, about average, it'll cost about $65 an hour to run with a 2-year depreciation. You can payback period. You can pay it back a little bit quicker or a little bit slower, but 2 years is pretty standard. Now, $65 an hour, if it's a 10-hour part, $650, not a problem. But a lot of metal parts run into the hundreds of hours. 100-hour for a part, $6,500. Now you start to care about, can we minimize that time in some way or another? So as I said, these figures are very rough, but they're pretty realistic in terms of what the cost is to run a machine. Now, these costs are not that different from a high-end 5-axis CNC machine or a high-end injection molding machine. The difference is on an injection molding machine, you inject your part in 1 second or 2 seconds or 5 seconds, as opposed to an additive manufacturing system where it takes hours or days to run the part, and that's why the cost goes so far. So a very, very simple example. This is a little hydraulic manifold. Basically, it's a block of steel with a whole bunch of holes drilled into it for your hydraulic fluids to go through. You drill your holes, you block where you don't want, and you're left with a set of interconnecting pipes to go through. So if you're going to print this in metal, this is what a slice will look like. It's going to look like a square. And imagine on a piece of paper with a pencil, you draw a filled square, you draw the outline, and then with your pencil, you hatch in the inside to fill out all the inside. Same principle along which pretty much all metal additive manufacturing systems work. You have your laser doing a hatch pattern, scanning the pattern to melt all the powder inside. So just some very, very simple numbers there. Let's say you've got a 0.1 millimeter hatch pattern. That's a spacing between the laser beams. They vary between just under 0.1 of a mil to about 0.15 millimeters. You've got about, for one 10 by 10 square, you've got about 100 meters the laser has to cover. If your laser is traveling at 330 millimeters per second, for a 100-watt laser, that's about right. If you have a 400-watt laser, you might be going at 1.5 to 2 meters per second. That means each slice is going to take 5 minutes to actually produce. So 5 minutes, that's worth about $5 per slice. If your slices are 50 microns per slice, you've got 2,000 slices in it, you're suddenly talking $10,000 to produce a part. Now you start to care about, well, can I design this to minimize that time? So if we look at this exact same design All I've done now is shelled the insides. I've produced the same part. It looks identical, but it's got a 2 millimeter wall thickness. The inside is all hollow. Now suddenly your slice looks like this. Your hatch distance has gone down to less than 5 meters. So that's almost a 95% saving in terms of the distance the laser has to travel, therefore a huge reduction on print time. And here we're down to 13 seconds. So we're down to over 5 minutes per slice, down to 13 seconds per slice. Huge saving already. And it'll look identical. Of course, the inside will be filled with powder or with support material that you may decide you can leave in or not, depending on how you want to do it. In contrast, if you redesign the part, so we take the same part, I've just done a shell function in it, which you can do in pretty much any software to remove all of the material that's not doing anything necessary, and said I want a 2 millimeter wall thicknesses, and that's what you're left with. Perfectly functional design, it'll do the job. You can set the wall thickness based on the pressure. So when you run this through your 3D printing software, this is the support material that will be generated. So for those of you not familiar with metal printing, you've got to anchor your part to the platform so it doesn't distort, the heat doesn't distort the whole part. This is the support material that is needed to weld the part to the platform. Now, nothing wrong with either of those designs. You might argue that if there's no reason not to, this orientation is maybe better than this orientation, because here you've got support material inside the part and removing support from internal structures much harder than from outside structures. Therefore, you could argue that the right-hand design is maybe better, but there may be a reason where the left-hand design is actually the better one, depending on your functionality. Now, if weight saving, if your only objective is to make your part as light as possible, that might be the final design ready to go. But maybe there's a reason where it's not all about weight. So here's one now. We've now redesigned it for additive manufacturing, where, for example, here before we had support material between the horizontal pipes. Now we've actually got a wall between the pipes to replace the support material. So that part is printable with no support material at all, other than what's welding it to the platform at the bottom. So very, very simply, cut it off the platform and you're good to go. Very, very little post-processing involved. So where it gets interesting, which is the point of the whole argument, is you start to look at the cost. Now, these costs down the bottom, these are actual quotes I got about 2 weeks ago from Sculptio, one of the online services that offers selective laser melting as a service. The standard block manifold, $15,000 to print a block of steel 100 by 100 by 100. That's heart attack material. And these are real prices. Now, I cannot think of any argument, no matter how complex it is, where a 100 by 100 block of steel is worth 15 grand. It just isn't. Contrast the shelled one, 3,700, and the designed one, 2,000, just under. I still think way too expensive, but that's because material prices are still better high. But this sort of makes the argument that you don't have a choice. You cannot print conventional parts that were designed for conventional manufacturing and expect them to come out efficiently for additive manufacturing. It's an absolute necessity. So here's a little example that we did just recently for Atlas Copco. Again, a hydraulic manifold. This is on one of the underground drilling rigs, and it's at the end of an extendable boom arm. So again, any weight saving we can reduce here is a huge advantage, because that means you can extend your arm further without needing as high motor. So this is the conventional design. Again, a block of steel. Here you can see the transparent section where you can see all the pipes going into it. This was redesigned into that, so it went from 14.6 down to 1.3 kilos. You can think of that in terms of weight saving. And again, from a design point of view, it was designed to be minimal support material needed. Now, these little pipes around here don't do anything useful. That's so when you put a spanner on it to tighten the hydraulic fittings, you've got some strength in it. And those require a little bit of support material. And here's the actual part as it's coming out of the printer with the powder still in it, and the part with the support material removed. So it just shows you that, with a little bit of effort in designing your part for additive, you can lose a huge amount of weight, but also the functionality was greatly improved. On the original manifold, the pipes came out at side angles because that's the easiest to drill the holes. Now we've got all the pipes coming out vertically, which means it takes less space in the machine, so you've got more space for other useful things. So you can not only save a lot of the weight, but you can improve the functionality as well. So I thought I'd give you another fun example of additive manufacturing. This is one I did about 2 or 3 months ago for a company up north called LaserTech. They wanted an executive giveaway, something to give away to people. So this is a little desktop distillery to distill your schnapps at your desk. Yeah, every person should have one of these. So the idea is you put your mash in here, your wine in here, ice cubes on top there, and you distill your schnapps while you wait. So it's It's the fun side of additive manufacturing. But again, it just to show that every exercise you do can be treated as a design for AM exercise. This is the actual design. So again, some of the things we've done is the spiral that you condensate the alcohol down has got walls in between to avoid needing support material between those coils. If I didn't have that, you'd have a whole bunch of support material, which would be a nightmare or almost impossible to remove because you just couldn't get to it. So again, the entire still is printed, just welded to the platform, cut it off, and you're good to go. So it just shows that with a minimum amount of effort, you can actually design your parts to be very, very cost effective and easy to remove. So in terms of opportunities, absolutely geometrically complex parts we know is a big advantage of additive manufacturing in terms of being able to produce parts that you could not produce any other way. Lighter parts, we've seen 2 examples of that already with the manifolds, part consolidation, tool-free, but to my mind, if you don't design for AM, you're going to get into trouble. So some examples of that. We talked about complexity for free. This is American Standard tapware. Beautiful, beautiful example showing complexity for free. And you think, how does the water get from here to there? And that's because with AM, you can make these complex pipes that you couldn't make any other way. Now, something to keep in mind, a set of these costs $12,000, so 120,000 crowns. So again, as I said earlier, high value, low volume is where AM is today. But the more you design for it, the better you can bring down the prices. So another example of design for AM, this is a little induction sealer we did for Tetra Pak last year. So it's a block of stainless steel. There's a copper coil in the top of it, and this is used to seal milk cartons. So you have 2 of these, you put your milk carton between them, bring them together, put a current through the coil, and induce an electromagnetic current which heats up the polymer that's coating the cardboard and seals it together. And in this case, on Swedish milk cartons, you have the little plastic screw cap. That's what this is for, so it can clear the plastic screw cap without hitting into it. Now, the way these things work is the faster you can cool them, the faster you can run the machine. Because after you seal a cap, it's hot, you need to cool it down before you can put the next cardboard through to cool it down. The way they do it today, they drill a hole, drill a hole, drill a long hole, block this hole, and now they can send coolant through it to cool it down. Standard way, the same way they cool injection molding tools and many other things that require cooling. Of course, one of the problems, this area here, no cooling. So you get a hot spot there where it's going to take longer to cool. So we redesigned it for them. The first thing we did, you can see it better here, we filled it up with a lattice structure on the inside. So it went from 320 to 160 grams, so half the weight, which may or may not matter. But a lighter product means the motors don't have to work as fast, there's not as much stress on the machine. But the big change was we now have a cooling channel that runs all the way across. It starts round over here, and then as it gets to this section here, it goes triangular, so you've got a wider surface area to carry the fluid going through. And if we look at the effect on that, here's the FEA on it. So the first thing we can see is the heat distribution. Here we've got a big hot spot of heat. Here we've got a nice even heat distribution across the top. So you get a better quality seal. And the big change, this is the temperature of the water exiting, or the coolant exiting the cooling channel. More than twice as hot here as it is here, which means we're removing more than twice as much heat from the product. So in theory, it means it should cool twice as fast. That's the finite element analysis. Tetra Pak are now in the process of building a few different designs and testing them in real situations. So we'll see if it really is the case. But again, it shows that just reproducing products the old-fashioned way, probably not worthwhile. But if you start to add value like this, you really can start to improve products. Again, this is a little bottle opener that I have on my keyring. This is topology optimization, and we have some companies here that do a lot of work with topology optimization. The idea is using mathematics to remove all the material that's not doing anything useful. So if we do an analysis of the table, we'll find 30, 40, 50% of the material from a structural point of view is not doing anything useful, so why not remove it? Same idea with this bottle opener. So this is rated at 300 kilos. Now, if you were going to make it the conventional way, you'd start with a block of, in this case, aluminium. Your block would weigh around 10 grams. You'd clamp it onto your CNC machine, and this would be your finished product that would weigh around 4 grams. You might be able to shave a little bit more off if you use very fine cutters. In contrast, you're down to under a gram for the topology optimized one. And you start to think about that in terms of weight saving, in terms of if you are building airplanes, now you're talking about serious added value by being able to reduce the weight to that amount. Now, 90% weight savings are pretty hard to achieve, but 30 to 60% weight savings, relatively easy to achieve depending on what it is you're doing. Part consolidation. Again, this is another big one, I think, from an engineering point of view. Being able to take a product made up of many, many simple parts, consolidating them together into a few much more complex parts. So this is a NASA rocket engine where they went from 115 to 2 parts. Those are the 2 parts here, which from the outside look pretty boring, but on the inside they're incredibly complex. You've got all the pipes, the valves, the louvers to direct the fuel where you need to. Incredibly complex. And this is because of that complexity for free. You can now make these incredibly complex parts that you couldn't make any other way. So as I said, being able to design for AM to take advantage of it is absolutely essential, in my opinion. So, a couple more before we finish off. To me, additive manufacturing's dirty little secret, post-processing. It's something when you buy a machine, it's something the sellers of the machine typically don't tell you about how much post-processing. So the imagination is you buy one of these printers, you hit print, and you get these perfect parts coming off. And whether it's plastic or metal doesn't make any difference. There is always a lot of post-processing involved. So what we talk about here is after it comes off the machine, the work you have to do to make your part usable. Could be something as simple as just coloring or painting the part or sanding it down to give it a smooth finish or tumbling it, for example, as the many operations. Companies like Daimler, EOS, Premium Aerotech, they estimate that 70% of the cost of the part can be in post-processing. So our earlier 100 by 100 block that takes 100 hours to print costs you $6,500. Let's be conservative and say there's 50% post-processing on that. You've now jumped it up to $13,000. So again, it shows you why it's so essential to design your part to minimize support material in particular. So support material for metal and for most plastics, so SLA, FDM technologies, you've got support material that has to be removed. If you can design your part to minimize that, huge advantages to be gained. So what we talk about when we talk about support material is this material here, between the jaws here, and the main reason for it to metal is somewhat to support the overhanging bits, but the main reason is to prevent distortion. Effectively, you're welding when you're printing with metal. You're welding, and if you weld a frame and you don't clamp it down to the table while you're welding this corner, that corner is lifting up and curling up. The same thing tends to happen with additive manufacturing. And in this case, these little spanners, so these, I've got this on my keychain. These are little spanners we did for a conference in New Zealand. It's actually a working spanner with moving parts, but all of this material here is what welds it down to the print platform, and in this case that has to be removed. Now some parts you can just CNC machine, some parts you can just wire cut off depending how they're designed. In this case the only way to do it is to manually break off the material, run a Dremel along the bottom to clean off the surface. The surface where it makes contact is always a bit rough, so you're going to have to do a bit of cleaning up on that. We had student slave labor, so it wasn't too big an issue, but it is something you need to consider when you do these things because it was for a conference. One more example of that, and I will show you one guitar. So this is a 3D printed aluminum guitar that I did about, I think about 8 months ago. So this is the guitar as it comes out of the machine, still welded to the platform. This big block down the bottom is a platform. That entire guitar is welded to it, and I've got a close-up of some of it. So there you go. That's a close-up of the support material. This is what's welding it to the bottom, and this is in between the barbed wires, even in the flowers, a bit out of focus, but we can see the support material in there. The only way to remove that in this case, you cannot, even if you couldn't even get to it with a CNC machine if you tried. So the only way to remove that is manually with pliers, screwdrivers, hammers, breaking it away, and then cleaning up the surface. Absolute nightmare. The result, if I may say so myself, pretty stunning. Almost a work of art, but when you look at some of the numbers on that, so the print time actually fairly reasonable. 9 hours of printing is all very minimal surface in terms of the hatching. The post-processing in terms of heat and stress relief, about 33 hours. Put in a furnace, heat it up slowly, then cool it down very slowly to get rid of any residual stresses and so on. And then 4 days to remove all the supports, and then another 4 days of filing, sanding to make it all look beautiful and nice surface finish. I've built 2 of these. The first one took me 4 days and 4 days. My hands were literally bleeding by the end of it. And in this case, most of the times when I order metal parts, they send me the metal parts with everything cleaned up. In this case, I asked the company Zylock in Belgium to send me the parts with the support material still on because I wanted to experience myself what a joy it was removing support material. But it's worth doing, because once you do it yourself, you really understand why you designed to minimize that support material, why it's so critical. So the second one I did took me 2 days and 2 days, so 4 days of post-processing. I'm guessing if I was doing a run of 10 of them, I might be able to get it down to a day and a half, but not much more than that, because it's a lot of work to get rid of all that material. So as I said, design for AM, it's an absolute necessity, not really a choice anymore. And just to finish off, what's missing in terms of AM being adopted by the masses, for want of a better word, we definitely need more materials. And I think at this event, we're going to be hearing a lot of weird materials, because Max 4 ESS type enterprises, you guys need a lot of strange materials that we wouldn't normally want to run. But it's a good area of developing new materials. Better surface finishes. Today, we're probably in this area here with the surface finishes. We need to be probably in this area here. And we're not there yet. Without massive post-processing, we're not in that area yet. Certifiable processes, so that when you print the part, you can guarantee the quality of the part every time. A lot of work going on in the area of qualification and certification. Better design tools, so better topology optimization tools, better lattice tools, better design for AM software that automates some of this for us. And absolutely down the bottom, better new engineering education programs, where within our undergraduate, even in high schools, we can start educating students and university students about design for AM as one of the new technologies that's there to take advantage of. So perfect timing. I'll leave it there, and happy to answer any questions if we have time for it. Otherwise, happy to discuss it over the coffee break. Thank you very much.
Thank you, Olaf. Thank you so much. And you're going to stay with us the whole day, right?
Until I've got a lecture at 1 o'clock, so I'll be here until lunch.
Okay, so and you're going to have your lunch with us as well?
Yes.
Perfect. So we have a lot of time to discuss with you. Thank you so much for a good lecture. What I understand from you, it's about, design freedom, of course, but also optimization, and you have to be quite creative.
Yes. You've got to find creative solutions. Yeah, yeah. So we always say you can print anything. Yeah, there's no limitations. In fact, there are limitations. Yeah. There's different limitations to with injection molding or casting or extrusion. So you've got to find creative ways of trying to work your way around those to keep the cost down, the quality up. Yeah. But
if you're used to design regular in CAD or so, what's the biggest challenge? Because this is a totally new way of thinking.
To me, the biggest challenge is really understanding and realizing. So support material is a perfect example. I would encourage everybody to get a part made in metal, leave the support material on, then remove it yourself. Okay. Then you instantly understand why support material is such a nightmare, and why, when you buy your parts, why the cost is so high. It's because the company has to charge you all those hours to remove the support material. If you do it yourself, you suddenly understand and say, oh crap, next time I'll design it to minimize that support material.
So less student slavery, more work yourself.
Yeah,
okay,
much.
got you. Thank you so much.
Thank you.